Buonasera, Atlanta Grandor Amici. It is a pleasure to join you tonight, and I'm looking forward to speaking with you about techniques in space-time physics for clean energy production. We all have a vision for a world energy solution that serves the greater good of human society and the planet. And today we're going to talk about world energy consumption, its implications to human society, are our global strategic plans working, and what are some of the potential solutions emerging in space-time physics, and also how we can all become part of the solution. Throughout history, we've seen individual consumption of energy increasing dramatically. As you can see on this chart, we show from the left primitive man, hunting man, farming man, followed by industrial man and technological man. And on the right axis, you'll see individual consumption of energy in gigajoules per person per year. And you can see as human society has evolved on this planet, energy consumption has moved from the consuming of energy just in the form of food to energy for cooking and heating, eventually for office work, trade and teaching, then industry and agriculture, and finally for transport, resulting in a dramatic increase and drain on world energy supplies. Another key factor we have to consider when we look at world energy consumption is not just consumption per person, but of course how many people. And this chart shows the increase we've seen in population just over a short period of a recent 100 years. In 1900, we saw about 1.6 billion people populating this planet, and today more than 6 billion. This number is growing quickly. And not only is the number growing quickly, but the percentage of the population, about 3/4 of the world's population, will begin consuming more as we move into the future, as they become more industrialized and technological in their local cultures and countries. And what we're seeing essentially is an increasing planet population combined with this industrialization that will dramatically increase world energy demands. And if we take a look at this, is not just happening in one part of the planet. What we see is energy consumption along the left axis, but if we take a look at the trends over a 30-year period, 10 years past and 20 years future, in the US and Canada, Northeast Asia, including Japan and Korea, India, East Asia, Russia, and the European Union, every region is projected to increase their energy consumption, in some places like East Asia and China on a very, very dramatic rate. Based on this present strategic direction, it's clear that the Earth's fossil fuels will continue to remain as the primary source for world energy. This chart shows very quickly world energy demand by fuel type. Along the left-hand side, we see the crude oil equivalent in millions of tons, and its usage based upon the type of energy technology from 1971 to 2030. And there's a couple things I'd like to point out about this. First, you can see clearly that renewable energy and hydroelectric power are not making the strides that many of the popular beliefs are that you'll hear in the political arenas and in the media today. Essentially, the projections from the experts are that, in fact, while the amount of hydroelectric power and renewable energy will increase, the percentage of its overall contribution to the world energy supply will decrease as we move forward into the next 2 decades. So the vision or destination is correct, but the strategic plan to get there is flawed. And as Albert Einstein said, the definition of insanity is doing the same thing over and over, expecting to come out different. And that's what we're caught up in now today as we look at our leaders, at governments and private institutions and organizations debating this and implementing plans. We're doing the same things over and over again, but that goal that we're trying to achieve in the future is not being advanced to. And simply put, the planet is accelerating along a path that will continue to deplete its resources. And if we take a look at these technologies like nuclear, coal, natural gas, and others, they are either intermittent in production, they have extremely high energy production costs, they use harmful materials, or even worse, they damage our ecosystem or create permanent hazards that will last for generations on our planet, which is unacceptable. One solution emerging in space-time physics is to go straight to the source, the same source that creates hydroelectric and tidal power. And essentially what we're looking at is taking energy from curved space-time naturally occurring around the Earth. This may very well be the next generation of energy that will come from the harvesting of the flow of space-time motive force across curved space-time. It's abundant in supply, naturally occurring and clean. It's highly efficient because we go direct to the source. There's no hazardous byproducts and minimal impact to the planet, even though I'd emphasize that more study is needed to understand the effect on our global ecosystem. But for those who are not familiar with the term space-time motive force or curved space-time, let's show it quickly in this a short description in this example. You can see the Earth. Anytime matter appears in the fabric of space-time, we know it distorts space-time around that mass. But also, as Einstein's special theory of relativity predicted, and we proved almost 25 years ago, is that as a rotating body spins, it actually twists space-time around it, like a spring. And that effect of twisting of space-time is called, in physics, inertial frame dragging. The potential energy stored in curved space-time around the rotating Earth, or any moon or any planet, is like a spring. And if that rotating body like the Earth were to be removed, that spring would snap back. The difference is that the potential energy that is stored in curved space-time is absolutely enormous. Now, how much is this inertial frame dragging? How much does space-time twist around a rotating body? Well, the answer is very, very small. If you take a look at this page, this slide, it shows a mathematical derivation of frame dragging, which holds accurate today. Frame dragging is very, very small, measured in the fractions of arc seconds, very small fractions. However, when combined with the kinetic energy of the Earth, the overall effect can be quite significant, measurable, and meaningful. As a matter of fact, the kinetic energy of our rotating planet is very, very large. If we take a look at the formula on the left for kinetic energy, considering the angular speed and moment of inertia, and we calculate it on the right, what we see is the period of the Earth being roughly about 23.93 hours with an angular velocity of 7.29 times 10 to the minus fifth radians per second, gives us a moment of inertia of about 8.04 times 10 to the 37th kilogram meters squared. That's roughly about 2.14 times 10 to the 29th joules. This is a massive amount of energy, and I'll try to put that in perspective, but first the question arrives, is it safe to harvest? As a scientist, I know, and we all know, that nothing is free, and that our planet is a complex system, and everything is connected to each other, and everything is interdependent on each other. We also know in physics and science of laws like the conservation of energy, which demands that there must be effect. If you take energy from one source, it must have a ripple effect across other parts of this environment. And of course, things will happen. If we harvest space-time motive force, some of the impacts, global tides would change, the Earth's rotation would slow, the orbit of the moon would increase, the weather patterns of the Earth could be altered. Would it be global chaos in the end of the world? Absolutely not, or at least that's what most experts agree. And let's put that in terms of an example.